The largest things in the universe are black holes. In contrast to things like planets or stars, they have no physical size limit and can literally grow endlessly. Although in reality, specific things need to happen to create different kinds of black holes, from really tiny ones to the largest single things in the universe. So how do black holes grow? And how large is the largest of them all? This video will not discuss how black holes work or how they form, since we've looked at that in detail in our black hole and neutron star series. You can check them out afterwards. For now, we're interested in finding the largest thing in the universe. Let's start really, really small. Primordial black holes. The smallest kind of black holes may or may not exist. If they do, they're probably the oldest objects in the universe, older even than atoms. They would have formed just after the Big Bang, when the universe was so dense with violent energy that any tiny pocket that was just slightly more dense than its neighbors could produce a black hole. The smallest primordial black hole that could still be around would be 8 trillion kilograms or so, the mass of a big mountain. And yet they would be no bigger than a proton. A primordial black hole with the mass of Earth would barely be larger than a coin. This makes them very hard to find, so we haven't actually observed any yet. If they exist, they may even be the mysterious dark matter that holds galaxies together. Let's move on to the kinds of black holes that we know for sure are out there. Stellar black holes. To make a black hole, we need to compress enough matter so that it collapses into itself. After that, the more mass we throw at it, the larger it becomes. In today's universe, only the most violent cosmic events can create the necessary conditions, such as the merger of neutron stars or when the core of a very massive star collapses in a supernova. To have a unit to work with here, we'll use the mass of our Sun, about 2 million trillion kilograms. The smallest known black hole has 2.7 times the mass of the Sun, which works out as a sphere around 16 kilometers in diameter, large enough to cover Paris. Another lightweight black hole is the companion to the V723 Mon red giant star. This star is 24 times larger than our Sun, 30 million kilometers in diameter. And yet, it's thrown around by a tiny black hole just 17.2 kilometers wide. This tiny thing bullying the star is so much smaller that we can barely even show them in comparison. One of the largest known stellar black holes is M33X7. It currently spends its time eating a 70 solar mass blue giant bit by bit. As all that stolen matter circles towards the black hole, like water going down a drain, friction heats it up to temperatures high enough to shine 500,000 times brighter than our Sun. And yet, X7 is only 15.65 solar masses and 92 kilometers wide, just big enough to cast a shadow on Corsica. To grow much larger, black holes have to either devour a lot of stars or, better, merge with one another. The instruments that make it possible to detect these mergers are very new, so we're currently discovering a lot of exciting things. Like 2 massive black holes that we detected in a galaxy 17 billion light-years away. As they spun around each other violently, they released more energy in the form of gravitational waves than the combined light from all the stars in the Milky Way in 4,400 years. The new black hole they formed is about the size of Germany and is 142 solar masses. And here we hit a curious gap in scale. There are lots of black holes up to 150 solar masses, and then there's nothing for a long time. Until we suddenly hit black holes that are millions of times more massive. Which is a bit confusing because we had this idea that black holes are consistently growing and growing. But for the most massive black holes, this process is not fast enough to explain their existence today. The universe is simply not old enough for these supermassive black holes to have formed by eating stars and merging with each other. Something else must have happened. To explain how we got the largest black holes in the universe, we might need the largest stars that ever existed, quasi-stars. To get a sense of scale, we can compare them to the largest stars that exist today. Our Sun is like a grain of sand next to them. We don't know if quasi-stars actually existed, but they're an interesting concept when it comes to supercharging black hole development. The idea is that the matter in the early universe was so dense that quasi-stars could grow to thousands of times the mass of our Sun. The cores of these stars might have been crushed by their own weight so much to actually collapse into black holes while the star was still forming. In contrast to stars today that would destroy themselves in the process, inside quasi-stars, a deadly balance could emerge. Gravity pressed the supermassive star together, feeding the black hole and heating the material falling in to such a degree that the radiation pressure kept the star stable. And so these quickly growing black holes might have been able to consume the quasi-star for millions of years and grow far bigger than any modern stellar black hole. Black holes several thousand times the mass of the Sun and wider than the entire Earth. These black holes might have become the seeds for supermassive black holes. So now we arrive at the kings of our universe, the largest single bodies in existence. The centers of most galaxies contain a supermassive black hole, and they are monstrous. In the Milky Way, we have Sagittarius A star, a supermassive black hole with about 4 million solar masses that is calm and collected and just does its thing. We know it sits there because we can see a number of stars being thrown around by a seemingly empty spot. And despite its incredible mass, its radius is still only 17 times our Sun. Smaller than most giant stars, but millions of times more massive. Because supermassive black holes are so massive and located at the center of galaxies, many people imagine them as being a bit like the Sun in the solar system, an anchor that glues everything else together and forces it into an orbit. But this is a misconception. While the Sun makes up 99.86% of all the mass in the solar system, supermassive black holes usually only have 0.001% of the mass of their galaxy. The billions of stars in galaxies are not gravitationally bound to them. Instead, it's the gravitational effect of dark matter which holds them together. Many supermassive black holes aren't gentle giants, especially when they're feeding on the clouds of mass in their galaxy. The one at the center of the BL Lacerti galaxy is devouring so much material that it produces jets of plasma accelerated to nearly the speed of light. If Earth were orbiting this huge body, it would seem 115 times larger than our Sun in the sky, and we'd be burnt to a crisp in seconds by its glowing hot accretion disk. At this point, black holes become so large that stars seem ridiculously tiny compared to them. The galaxy Cygnus A has a supermassive black hole with 2.5 billion solar masses and 14.7 billion kilometers wide, which would mean that if it took the place of our Sun, it would swallow all the planets and stretch halfway to the edge of our solar system. It's devouring so much mass and material that it churns its disk into a kind of magnetic funnel, spewing gas out, making tremendous radio lobes towering over the galaxy 500,000 light-years in diameter. That's 2.5 Milky Ways wide. Another pretty large supermassive black hole sits in the galaxy Messier 87. It has 6.5 billion solar masses and was the first black hole we got an actual photo of, or rather, of the glowing gas around the edge of a menacing shadow. This sphere of darkness is so large that it covers our entire solar system.
Can everyone hear me? Can everyone see me? Sorry, I'll try to pull a Gilderoy Lockhart. Okay, okay. Are you sharing the screen, Julia? Okay.
I don't think they can. Screen PowerPoint.
Screen.
Okay. Do you know?
Not ready.
Okay.
Okay, hello everyone. Okay. Okay, hi everyone. Sorry for the delay. We had a bit of technical issues. Today is going to be a very general welcome to astronomy kind of lecture. I'm going to go through what is astronomy, bit of history, uh, what astronomy isn't, and then we will go out for observation if the skies permit. All right. Before we move on, I'm Sharat. I'm Astro Head for the 24th Exco, and thank you all for attending both in person and on Zoom. All right. Any questions we will try to answer as we go. All right. So without further ado, let's move forward. Why is your not working? Okay, I just had to move the cursor over, right? No problem. All right, so what is astronomy? Astronomy is not astrology, okay? It's actually a multidisciplinary science, right? If you want to do a very interdisciplinary, very so-called CHS kind of in the spirit of CHS, right? Astronomy fits it all, right? Because you have physics, you have chemistry, geology, biology, geometry, obviously mathematics, because physics and chemistry has roots in mathematics, as does geometry. And astronomy is not astrology, right? Astrology is we'll go into exactly what astrology is in the next slide, right? We'll have a very brief tangent to astrology. It is an offshoot from ancient times, from older times when people didn't really understand what the universe was about, and science didn't really exist in the formal codified form that it does today. Right? People believe that this natural occurrences were caused by gods. For instance, you had a thunder god, you had a rain god, you had a fire god. In the same way, they thought the planets themselves represented the gods and goddesses, which is why technically they are named after Roman gods and Greek gods and goddesses, of course, right? And the key reason why it sustains to this day is because people are generally afraid and unsure of the unknown. And the future is unknown. So that's why people still like or still follow astrology. Right? This is my view of it at the very least. Right? The idea behind astrology is that the position of the sun in the zodiacal constellations, of which there are 13, defines your birth zodiac. For instance, Gemini, Leo, Pisces, Cancer, whichever. These are real constellations, by the way. So if you pull up a star chart or something, you actually see patterns of at least the star chart will show you patterns of stars in the sky. And these are named after Greek heroes, myths, imagery in general, right? We even have more modern constellations like telescopium, which is a telescope, and ancient Greece didn't have anything in the way of telescopes, right? Of course. And furthermore, the positions of planets in the various zodiacal constellations supposedly affect, your behaviors, how you interact with people, any windfalls, any fortunes, any misfortunes, right? You see, there's a zodiac section in nearly every newspaper. Most of it is bunk, but it's fun to read. It's interesting to read, right? And that's why people still follow it. And from what I understand, a lot of people still do follow astrology, not just because they believe in it, and more so because it's a little bit fun as well. So yeah, well, the whole thing is a bit sus anyway. So let's move on. So now let's go to astronomy, right? Right, we have ancient people looking at the stars, right? This is I said Aristotle. That's ancient by way of how like civilization in general is ancient, but prehistory, right? It's said that astronomy is amongst the oldest professions. There are a lot of oldest professions. There's teaching, there's soldiering, there's a few more sus professions like thievery, so on and so forth. Astronomy is in that list, right? Because when it gets dark, you can see the stars. Not in Singapore, but probably about 2,000 years ago when there was no city lights, you probably could see like a lot more stars than you can today. And then you have geocentrism, which was codified by this guy called Claudius Ptolemy. Basically, it put the Earth at the center of the universe. And humans, being the very egocentric people that we are, followed this for about 1,500 years. Right? It was not until relatively recently in the history of science that things began to change. And we have Galileo Galilei, who substantiated heliocentrism. We'll get to what this is in a short while. With telescopes. Galileo didn't invent the telescope, incidentally. I forgot who exactly did, but he did make good use of the telescope to prove that geocentrism was wrong. Uh, and this is some art of Galileo peering into the sky in Italy. And this is some of his drawings. We'll see this again in a short while. And we'll go through a very brief history of astronomy. I just gave you a very quick summary. We'll go into a bit more detail shortly. Right, this is what we have for today. So prehistory, the ancient world, right? We have Stonehenge. We have this little plate over here, the Nazca lines, and like I mentioned, the Roman and Greek gods. Stonehenge is about 5,000 years old-ish. The exact date is not confirmed because it's so old. People place it at 3000 BC, which is 5,000 years old. And its exact purpose, while not known, it is suspected to be some form of observatory. Right? In general, when you have a very random a very geometric pile of rocks, people generally think it might be something that aliens put there, but the explanation is almost always a lot simpler. Chances are it was an observatory. It was to do some kind of survey around the land, something like that. Right? And Stonehenge is in England, by the way, so it was put there by the very ancient English, way before, Richard the Lionheart, or Arthur, or King Arthur, or King Alfred the Great. It was eons ago. Chances are England was still connected to Europe by a land bridge back then, because it was 5,000 years ago, right? On the top right, you see the Nazca lines. The Nazca lines are in South America, uh, in Peru, I think, and Peru or no, in South America, on the western side of the Andes. There's a very big desert. And over there you can see a spider. There are a lot more weird animals. The scale of that is about, I think, 300, 400 meters. People, again, modern conspiracy theorists suggest that they were put there by aliens. But again, the explanation is a lot simpler because they aren't that old. This is about 1,500 years old. But it's prehistoric in the sense that North America and South America developed a little bit later than Asia, Africa, and Europe in terms of civilization. And again, the explanation is that they charted the stars. They were interpretations of the stars, or their own interpretations of the gods. How they put them there was also demonstrated by modern scientists. The theory goes that, oh, this is so big. How can you get people? How could people so long ago plan such a beautiful geometrical drawing in the middle of the desert? The thing is that people could and people did. Like 1,500 years is not that long ago. We had the pyramids 4,000 years ago, and those are huge. Those are gigantic undertakings. So, moral of the story is that generally you get people to work together, you can achieve things that seemingly seem impossible for the time. Right. Okay. Looking at the plate on the bottom left, that is actually the Pleiades. This was found in Germany, if I recall correctly, right? And it is about 3,000 years old as well. And that's the sun, obviously, that's the moon. The little cluster of stars on the top right, on the middle top right-ish, is the Seven Sisters or the Pleiades. Right, and now we have the Greek and Roman gods and goddesses, which is where we get the names of our planets from. The word planets itself comes from the word planetes, which in Greek means wanderer. Compared to the rest of the stars, the planets move very obviously, and they are a lot brighter than the rest of the stars. So the Greeks and Romans obviously noticed, hey, these are different. They are different in some way, so they call them wanderers because they move, right? So we move on to classical geocentrism, which is the theory that endured from classical antiquity, about 500 BC, to about 1500 CE. The first guy to prove that the Earth was spherical was Eratosthenes, right? He had a very interesting method to do it. Basically, he put two big posts in two different cities, Alexandria and Cairo, I think, or Athens and Alexandria. I can't recall which. And he compared the shadows on the two posts. He ensured that the posts were straight up. So if the Earth is a sphere, right, the shadows must differ by some amount. And he calculated a value for the circumference of the Earth, and he arrived at 44,000 kilometers. Actually, a very decent estimate. It's only about 10% off from the modern value, right? So maths back then was pretty good, right? Take that, flat earthers. And now we come to the whole concept of exactly what geocentrism is, right? These images pretty much portray the idea of geocentrism in that there were shells around the Earth, of concentric shells around the Earth where the planets and the sun were embedded into. And it was said that the Earth is impure because we filthy humans, are on the Earth, and the heavens are perfect, right? And the stars are like there are different interpretations of what the stars were, what the planets were before science, before at the very least Galileo. Right now we have heliocentrism, and this guy is Nicolaus Copernicus or Nikolaj Kopernik, uh, Eastern European name, but most people tended to Latinize their names back then. I should Latinize my name, Sharadas Rajaramanus. Uh, the problem behind geocentrism is that it was extremely complex, right? And there were some issues with, or at least the observations back then were accurate enough to tease out issues with geocentrism. The fundamental idea is that the Earth is in the middle, everything orbits around the Earth, which is how it appears to us, right? We are on flat ground. Relative to us, the sun moves around us, the skies move around us, the planets move around us. That is the naive or immediate assumption that most people will make. However, this uh, after more careful observations, after more careful timekeeping mainly, and calendar making, people realized that things were off, right? Geocentrism didn't really apply or didn't make sense, had errors, more importantly. So Nicolaus Copernicus introduced heliocentrism. Incidentally, geocentrism, the word geo means earth, centrism in the center. So geocentrism means earth in the center. Heliocentrism, helio comes from the Greek word helios, which puts the sun at the center of the universe. Now, just saying, neither is at the center of the universe. We are on a random planet, orbiting a random star, inside a random galaxy, inside a random point in the universe. Right? So we are not really that special. Or at least the planet we live on is not really that special. We get to what life is in another lecture. That is a whole other can of worms. Right. And this kind of applies, Occam's razor. Keep it simple, right? The simplest explanation is probably the most likeliest explanation. And here I kind this give explains how absolutely complicated geocentrism gets after a while compared to heliocentrism, right? Notice that heliocentrism still doesn't really represent some key problems, which Einstein later solved. We'll get to that in about 2 slides, right? And Galileo, right? This was a plot by Galileo. He very interestingly pointed a telescope at two very key objects in the night sky, very visible objects in the night sky. First of all, he pointed it at the moon. The prevailing interpretation of the moon's various dark and light spots was that the moon was a perfect polished mirror-like object, and it reflected all the imperfections of Earth. But then Galileo pointed a telescope at the moon. You don't need a very big telescope to see what he saw, right? It's the estimate is that he used probably 200, 300 millimeter telescope. I can't recall the exact number. We just need a relatively small telescope to see that the imperfections on the moon are actually geological features on the moon itself, which was the first sign of evidence that we are not special. There's nothing unique about us. There's geological features everywhere. Earth is not impure and the heavens are not perfect, right? Next up, he pointed his telescope at Jupiter, right? And he resolved both the circle of Jupiter and its bands, right? Which is why Jupiter appears as a circle here. It's fairly easy to make out the circle, by the way. You don't need a very big telescope. You probably can do it with a pair of relatively decent binoculars. Jupiter is very big. And he also saw the four moons. And he plotted this little graph image over here, which proves that other objects orbit Jupiter, and if other objects orbit another planet, right? Surely, all the other planets also have, everything orbiting it, and therefore, why should everything orbit us, right? That was the logical leap of thought that he made. Right, and now we come to Kepler and Newton, right? I'll go through this very quickly because this is a lot more physics than it is astronomy. Long story short, Kepler and Newton together derived the mathematics required for heliocentrism, right? Again, I mentioned that the mathematics is incomplete, at least insofar as Mercury is concerned. We'll get to that in a short while, right? The long and short of it is that we have the three rules over here. All planets move around the sun in conic sections. The sun is at one focus of the section. A line joining a planet and the sun sweeps out equal areas over equal intervals of time, and the square of the period of the planet, basically how long the planet takes to orbit around the sun, squared, is proportional to the cube of the semi-major axis of its orbit. In general, in layman's terms, we can think of it as approximately equal to the radius of the orbit, right? It is not strictly the radius of the orbit, but take it as it is for now, right? And these are his three laws of planetary motion. And Newton's laws of motion and universal gravitation work with these, so you can derive Kepler's laws from Newton's laws. Pretty nice, right? And these laws are taught in physics to this day. These are about 450 years old. It kind of proves how iterative science is, which is very nice. If you're interested as to what conic sections are, the top left shows you what they are. And the blue area, right, is constant area, which shows that the further a planet is, like the slower it moves from the sun. It applies to not just planets and the sun, but anything in orbit around anything much more massive as well. And at the bottom, we have Newton's law of gravitation. Right, and now we come to finally, in the middle, there was a lot of discoveries like 1700s, 1800s. We discovered three new planets, right? We discovered Uranus, Neptune, and we discovered Pluto, which was subsequently demoted from status of planets. We also have discovered a lot more minor planets as well, right? Which is why Pluto was demoted, which is a big contributor to why Pluto was demoted. And okay, amongst the audience and on Zoom, how many of y'all have watched Interstellar? How many of y'all have watched Interstellar? Came out in 2014, quite old, fairly old movie. How many of y'all understood Interstellar? More important question. Okay. I'll try to explain the movie. It's a very long movie. It's a very interesting, quite sad movie as well. Okay, not sad, but bittersweet kind of film. The long and short of it is that gravity and speed affect how light interacts with things. I'm not going to go into the maths. The maths is painful, extremely painful, as anything to do with Einstein is, right? Why can't I click? Okay. Right. Like I said, Interstellar is confusing, right? He basically tells us that space and time are not two separate dimensions. Usually, we'll say, "Oh, he's at this time he was doing something, and at another time he was doing something." Einstein tells us that space and time are one thing, right? Called space-time. And well, likewise for electricity and magnetism, but that is a more tangential thing. He basically says that the faster you go, time itself travels uh, slower for you, right? For an observer, let's say you're on a train traveling like near the speed of light. An observer would see a clock on the train travel a lot slower. This is called time dilation. Right? Interest very 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 mind blowing. The key principle behind this is more importantly that the speed of light is constant, right? In all frames or in all from all perspectives. So you can't really break the speed of light. Consider a very simple thought experiment, right? You are stationary and you throw a ball, like at some speed, and you're on a bus and you throw a ball at the same speed. Clearly, the ball that you throw from the bus is faster, right? But the interesting thing is, if you shine a lamp, stationary and on the bus, the emitted speed of the light from the lamp is the same in both cases. How is this the case? Because time slows down, right? Which is very interesting. And the effect is measurable and affects our daily lives. Okay, not just speed, but gravity as well. GPS makes use of it. The error is sufficient enough that after about an hour, your GPS error is about 200 meters, 100 to 200 meters, which makes it useless. And after about 2 hours, it's almost a kilometer away, which is completely useless. Right? And this is the whole idea of general relativity. And this was the final correction to astronomy and astronomical development as a whole, because it accounted for Mercury's orbit. The interesting thing about Mercury's orbit is assuming this lamp can be the sun. How do I switch this on? Okay, assuming this lamp is the sun, and assuming this lamp is Mercury. This lamp doesn't work. Okay, fine. This lamp also went out. Never mind. Okay, assuming my left hand is the sun and my right hand is Mercury. The orbit went like this. So the longest part of the orbit itself shifts, and Newtonian mechanics couldn't account for it. Einstein found a solution, and that's called general relativity. He also introduced or co-introduced other new concepts, including quantum mechanics. So the whole idea of platform 9 3/4 is that you can magically move through. If you're magical, right, or if you're a magician, you can move through the barrier, right, and go into a new platform. That's kind of the idea of quantum physics, right? You can magically tunnel through barriers, right? And it contributes to the phenomenon that powers our stars, which is nuclear fusion. Right? Without quantum tunneling, you wouldn't have nuclear fusion, you wouldn't have the sun. And in general, astronomy today has taken on a whole new phase. Right? Back then, it was your science. It's not just astronomy, actually. Pretty much all science, but astronomy especially, because it's it's very interesting to see. It's not just your solo scientist in a dark room poring over his books and then pointing a telescope at the sky. And, oh, I discovered something new. That's pretty much how excuse me, Uranus and Neptune were discovered. They were solo efforts, right? Today, astronomy requires multi-10 billion dollar efforts in the case of the James Webb Space Telescope, which is launching this December, right? It is a huge, expensive undertaking, right? It requires terabytes of data, lots of data processing, and now we have private space entities as well, right? And there's a lot of very interesting things going on with SpaceX, Blue Origin. We saw like private launches to space just earlier this year. Very interesting, and this is a completely new facet to astronomical and cosmological observation. About 50 years ago, actually not even 50 years ago, about 30 years ago, was primarily a government-funded thing because only governments could get big enough and could sponsor enough money to make these observations, to make these monumental feats of technology possible. But now, astronomy has become commoditized, especially in the case of citizen science, right? There's this thing called BOINC, where you can contribute to, you can use your spare processing power. Like, if you happen to leave your computers plugged in and switched on at home, right, you can use the computer as like spare processing power and contribute to big science projects. One very interesting project of BOINC is SETI, Search for Extraterrestrial Intelligence, right, which basically scans the sky for radio waves, for patterns in those radio waves, breaks up the scans into manageable chunks, sends it to different computers, and lets different computers process this and return the data back to a central server to combine. This is called distributed computing. But it is how astronomy has become very multidisciplinary nowadays. I mentioned geology and biology. That's where extraterrestrial, and chemistry, of course. That's where extraterrestrial, the whole extraterrestrial idea comes in, right? It's a relatively novel concept, right? So the idea of aliens just didn't exist before about the 1950s or so, right? And it was, even then, it was strictly in the realm of science fiction. Today, amongst most scientists, there is consensus that chances are we are not the only life out there, because the universe is so big, right? Like, and again, the prevailing consensus is that life arose spontaneously, right? Because life is essentially just forming patterns, right? And nature likes to form patterns. We'll get into this in another lecture probably, right? But in summary, the face of astronomy has changed, and the future holds a lot for astronomy, right? And I'm not sure about you guys, but I definitely look forward to how things will, especially the introduction of private enterprises and citizen science will change the whole face of astronomy. We can do it too. We do it too at NUSAS, right? The fact that we have sidewalk astronomy, the fact that we have these lectures in the first place, is an example of citizen science and outreach. And we hope that we'll continue this a lot more in the future. Right? Thank you. Okay, I have a very short Kahoot quiz. Let me just blank the screen and get it. Julian, can I have some help?
So,
Okay, it's on Kahoot.com. Just take the latest quiz. Welcome to astronomy.
very short.
Thanks so much, man. Yes. Thank you so much. Bro, this week has been freaking headache for me, bro.
How do
You need to go to Kahoot.com and then share the thing. You need to log in. Let me pull up the spreadsheet. The NUS Astro email. And then this is the password. M40, capital M41 at gmail.com.
the mic is still on, so
Capital M42.
I'll just see yours.
Should be the latest one. You click again. Okay. Welcome to astronomy. Let me just double check the quiz. Six questions. Very short.
What's right?
Okay.
Oh, okay.
Levels is better.
I can close the slide.
Just F12. Just F11. Alright, so can we request those in the lecture theatre and those on Zoom to join this quiz? pretty easy. The plan is that we are planning to collate points over the semester and probably have like sweepstakes or a grand draw. Hey, close the thing.
It's exiting.
6801673. Right, so as I was saying, we plan to collect points over the semester. We don't have prizes immediately. And we do have refreshments though, which is also a very good initiative. Yes, we will collect the points and we hopefully can get your names as well. And we will combine them and maybe at the end of the semester we will have a grand prize type thing. Okay, so
Zoom has sensory money. Yeah.
can you not? Can you not? I know it's you. Why not? Okay, about 20 more seconds. Wait for more people to join. Start. Thank you.
Oh, the hell.
Okay, I think we can start. Right? Not really. Right.
Exit full screen.
Okay. This is a case of one is more correct than the other.
You can put multiple correct answers.
Okay. That's true. That's a good point. But yeah, fair point. Okay. Next question. Congratulations, Esther. Go.
Brian.
I mean, the life bigger.
Okay, I understand. It gets a bit difficult. I'm not gonna lie. It's difficult. It's difficult to keep attention for too long. The starting part is the more interesting part. Right. Thank you. Finally. Oh, who's Matt?
What happened to the last one?
Okay, I think that one popped up. I had an option, but then when I saved it, it disappeared. Please don't, please nobody select call.
God, this is so bad.
All right. Okay.
Any more questions?
Special. What the?
For a mouse.
Okay. All right. Congratulations on Pluto, not a planet. Max. Alright, we'll collect the points and hopefully at the end of the semester we have something very nice planned for you guys. Thank you. And that will be the end of the indoor segment of today's session. Right. Please head out for observations. Thanks and have a nice evening. Cheers guys. Bye bye.
Going into the sure. Later you get at night in the morning.